Our molecule's journey is going to happen in 5 main stages. First, we'll get a handle on the challenge itself, what we're trying to fix. Then, we'll follow its intense prep work on the path to reaction. After that, we'll witness the big moment of transformation inside the catalytic reactors, see how all the results get sorted out, and finally, watch it become a pure, finished product.
Okay, so let's set the stage here. Refiners are often left with these really heavy, complex, and, let's be honest, pretty dirty parts of crude oil. This stuff called vacuum gas oil isn't very useful by itself, but locked inside its big, bulky molecules is the potential for really high-demand fuels. The whole challenge is just, how do you unlock that potential?
And that brings us to the big question this entire massive unit is designed to answer. How do you take these huge, clunky molecules that are full of impurities and precisely break them down into the clean, efficient fuels that, power our world? Well, the answer is a combination of brute force and some really elegant chemistry.
And that answer is hydrocracking. The best way to think about it is like a recipe with 4 absolutely crucial ingredients. First, you need immense pressure. Then, you add a ton of heat. You mix in a huge amount of hydrogen. And finally, you pass all of that over a special material called a catalyst, which is kind of like the chef that makes the whole transformation happen without getting used up itself. Now, to really grasp the scale of this upgrade, just look at this comparison. We start with a feedstock that's got over 2.5% sulfur. The goal? To make diesel with just 10 parts per million of sulfur. That is a reduction of over 99.9%. So we're not just cracking molecules apart, we are performing an intense purification at the exact same time. It's incredible. All right, our molecule is now about to start its physical journey. But before it can actually be transformed, it has to be prepared. And it has to run a kind of gauntlet of equipment, all designed to get it into the perfect state for the big reaction. Let's see how they do it.
This whole preparation process happens in 4 key steps. First, it gets cleaned up. Then, it gets squeezed under some truly unbelievable pressure. After that, it gets preheated using a very clever energy-saving trick. And then finally, it gets that last blast of heat it needs to be ready for the main event.
The journey kicks off at the feed filters. Think of these as the bouncers at the door. Their whole job is to pull out any solid gunk, anything bigger than 20 microns, from the oil. And this is an absolutely critical first step, because that catalyst downstream is the heart of the whole unit. It's super expensive and very sensitive. Clogging it would be a total disaster. Next up, pressure. Once it's clean, our molecule gets slammed into these massive, multi-stage reactor charge pumps. These things take the feed and crank the pressure all the way up to 195 bar. Now, to put that into perspective, that is over 190 times the pressure of the air you're breathing right now. This insane pressure is what physically forces the hydrogen and oil molecules to get up close and personal for the reaction.
Okay, with the pressure way up, it's time to add heat. But instead of just burning a bunch of fuel, the system does something brilliant. The cold, high-pressure feed is sent through a whole series of what are called feed effluent exchangers. In here, it flows right past the scorching hot products that are leaving the reactor. It's this fantastic energy-saving loop. The hot stuff heats up the cold stuff, recycling energy that would otherwise be wasted. And for the final step in prep, our preheated oil mixes with superheated hydrogen gas inside the recycle gas heater. This furnace provides that last, critical temperature boost. It gets the whole mixture to the precise temperature it needs to kickstart the reactions the very second it hits the catalyst.
So the prep work is finally done. Our molecule, now super hot under massive pressure and mixed with hydrogen, is about to enter the heart of the hydrocracker, the catalytic reactors. This is it. This is where the magic happens. This is the moment of transformation. Inside these giant, towering reactors, the mixture flows down through these packed beds of catalyst. And as our molecule tumbles through, 2 really important reactions are happening. First, a process called hydrotreating literally rips impurities like sulfur and nitrogen atoms right off of it. Then, hydrocracking snaps its long carbon chain into smaller, more valuable pieces. So you might be wondering, why not just use one giant bed of catalyst? Well, it all comes down to some really clever engineering. Splitting the catalyst into multiple beds helps make sure the oil and gas spread out evenly. It also creates these empty spaces where they can inject cold quench gas, which is just recycled hydrogen. This gives operators really precise temperature control and stops the reaction from getting too hot and running away. Okay, the reaction is complete. Our original molecule has been totally broken apart and purified. But now it's just one part of a chaotic, superheated, high-pressure mess of gases, valuable liquids, and byproducts. So the next stage is all about carefully cooling this mixture down and sorting everything out. This separation happens in a few stages. The mixture first gets cooled down a bit. Then it goes into a hot separator. After some more cooling, it goes into a cold separator. And then finally, the liquids that have been separated out get sent to flash drums. Each step is designed to pull a different part out of the mixture. So let's follow the flow. After leaving the reactors, the stream heads to the hot separator, and that's where the vapor and liquid phases split for the first time. The vapor then gets cooled and enters the cold separator. In there, contaminated water, they call it sour water, condenses and gets drawn off. And finally, the leftover liquids go to these flash drums, where a sudden drop in pressure makes all the dissolved gases literally flash out of the liquid. Now remember all that hydrogen we added at the beginning? Not all of it actually reacts. And that unreacted hydrogen is way too valuable to just throw away. So it's collected and sent to a massive piece of equipment called a recycle gas compressor. It repressurizes the hydrogen and sends it right back to the start of the process. And to replace the little bit that was used up, fresh gas gets added by makeup gas compressors. It is a critical, continuous loop that keeps this whole thing running. We have finally reached the last stage. The gases are gone, the sour water is gone, the hydrogen has been recycled. What we're left with is a mixed stream of liquid hydrocarbons, all the good stuff from the cracking reaction. Now, in the fractionation section, this valuable liquid is going to be meticulously sorted into pure on-spec products. And the goal here is perfectly laid out in the operator's guide. It is necessary to separate this stream into the desired products, such as light gases, LPG, gasoline, kerosene, and diesel oil. I mean, that's it. This is the final refinement, turning one mixed liquid into multiple, distinct, and very valuable streams. This final separation takes a whole train of distillation columns. First, the liquid goes into a stripper column, which uses steam to get rid of any leftover hydrogen sulfide. Then it's fed into the main product fractionator. Here, everything separates by boiling point. Lighter stuff rises, heavier stuff falls. Kerosene and diesel are pulled off the side as side cuts and sent to their own little strippers for fine-tuning. And finally, the raw gasoline from the very top goes to a debutanizer, which gets rid of the lightest gases to make it stable. And the result of this entire journey, well, it's pretty stunning when you look at the numbers. We started with a heavy oil that had over 2.5% sulfur. Our final diesel product has just 10 parts per million. We've also created a super high-quality fuel with a cetane index of 62, and that's a key measure of ignition quality. Basically, higher numbers mean a more efficient and cleaner-burning engine. It is a complete and total transformation. So our single molecule started its journey as a tiny part of a heavy, dirty feedstock. It survived extreme pressure and heat, it was cracked open and purified by a catalyst, and then it was meticulously sorted from all its neighbors. And in the end, it became a key component in the clean, high-value fuels that are pretty much essential to our modern lives. This incredible dance of physics and chemistry is really a marvel of 20th century engineering. And it's still the backbone of how we produce clean fuels today. And that kind of leaves us with one last thought. What's going to be the next great chemical engineering challenge that defines our energy future?